Section 22 is taking all the ideas of circuits and looking at what are called parallel and series. The most fundamental setups of all circuits are parallel and series circuits. Now, if you were to actually look at a circuit and you were to actually break down, say, the circuit that goes through this room providing electricity for these lights, you'll notice that there are things that are in series and in parallel, both. Okay, so when I say series or parallel, a lot of circuits are going to have both series and or parallel in there. Now, what we're going to do with two major objectives is to calculate what's called the equivalent resistance, so the overall resistance. Remember yesterday when we did that problem and I said, find the overall resistance of the television if it was like a given power and a given power and a given voltage. That's what we're going to be doing. Imagine you have a bunch of different resistors, like all these light bulbs, and you need to know what the whole system is as a resistance in order to know what to apply as a voltage. We're going to do that in the first part. And then we're going to find the current in and the potential difference across each resistor in that circuit. Okay, so let's start with the first. We'll take a look at types of circuits. So, anybody remember, what the heck's the movie? The one with the Christmas movie where the lights keep going out?
National Lampoon.
National Lampoon's Christmas Vacation? You know how the lights keep going out and stuff like that? And then one goes out and then suddenly they all go out? Well, the simplest way to remember series circuits is this. If one of these bulbs went out, would that circuit still exist? Like imagine this bulb was suddenly not working and electrons couldn't pass through it. What would happen to all these electrons that are trying to get to the second bulb? Would they ever make it there?
No.
So if one bulb goes out in a series, what about parallel though? Look at parallel.
Well, I'm thinking Christmas.
Look, but odd. Yeah, it's like a Christmas tree. Ever break a bulb in your Christmas tree lights and they don't all go out? That means that it's in parallel. And think about it, watch. If this bulb breaks at the top, suddenly all of these circuits are still hit, except it just doesn't make it up that last loop. All right, think about the orientation. It starts here. Follow my fingers here. Goes through the first bulb. Comes up here. Goes through the second bulb. Through the third bulb. Through the fourth bulb. And each of these junctions has a specific characteristic about it. And we'll talk about the currents and how they work there. Okay, but the idea with a parallel circuit is that when one of the elements is no longer in parallel, the circuit still exists or it still is closed. Think about like removing one of them. If I just went like this, ready? That's gone, right? Now follow the flow. Still goes through here, through here, through here, back out. It still has a path to flow. Whereas here, I remove this. How can that electron literally go from there to there? It can't, right? It can't go any further than right here. Because to get to this bulb, it can't just jump the gap. There's a gap here now from this bulb that's being created. But the gap that's up here at the top that's created doesn't really affect it because these are still all connected. We're going to do this in the lab and it's a little more obvious that they work. But think about the fact that if you had pipe flow. Imagine water flowing through a pipe in a series setup. If there's a break in that pipe at the end, what's going to happen? There's a break right here and there's a water source here. All the water is going to go out of the pipe, right? Imagine, okay, let me make it a little more clear. There's a waterfall, or there's water coming down a stream, and there's suddenly a big ditch off the side of that stream. The water is going to get pulled to the side, right? If suddenly there was like a gap that it couldn't surmount, like the water literally would fall into like a giant pit, it's like a series circuit. As opposed to like a parallel circuit, think about this setup here with water flowing. Remember, water's flowing, it's flowing through. Suddenly there's an opening out here. Some of the water might get out, but a lot of that water would still continue in the circuit, right? It would still have other paths of resistance that it could travel on. So when there's an element removed in a parallel circuit, it's like it's not there. It's like that wire didn't exist. Imagine getting rid of that wire. So everywhere where you see the wire, I'll zoom in so you can see it better. Okay, everywhere you see this wire, it no longer exists. That's what would happen if you remove that bulb. Well, the circuit is still complete. It's not a short circuit. Follow it from beginning to end. Again, follow it from beginning to end. Starting here. It goes through the circuit, goes through this wire. Part of the current goes up, part of it goes this way. It goes through that bulb, comes back. The part that goes up here goes here. But then part of that current that went here splits off and goes up here. And part of it goes up to the top. So the current splits off at these junctions. And part of the current goes to each of the bulbs. Okay, but there's no opening in the circuit when you remove a bulb in parallel. When you remove a bulb in series, there's now a big opening right here. It's like, okay, I'm flowing, and then stop. And then there's a big gap right there. It can't just jump over that gap.
So, but if the first bulb in the parallel one goes out, it won't matter?
It won't matter either. Yeah, they still work. Let's take a look at that.
Wait, but like, what if like the middle one stops
There we go.
working?
Still would work. I know. Hold on. Let me show you. Let's take a look at the circuit without it.
Why would anyone use a series circuit?
Because, and that's the part we're going to talk about really in the next lesson, but the combination of series and parallel is widely used. Nobody really uses just a series circuit anymore, but the combination of the two is very important. It has to do with controlling the amount of current in the circuit. Series and parallel circuits have different currents as a result of their orientation. If you want a specific current in your circuit, which you do a lot for things like computers, you want it to be set up in a certain fashion. So it's usually a combination of the two. This is just a basic look at what it really is. So here, remove this one, right? Everybody, remove this. Remove these wires. It's still connected, right? Follow, watch. Starts here, flows up. Part of the current goes up here, part of it goes into this light bulb and comes back. The other part, though, continues. And instead of going here now, because there's nothing there, it continues up. And it goes here, and it comes back. And then part of it actually continues all the way up, goes all the way to the top, flows through, and comes back. So every time you see a juncture, think about water in a pipe. The water in the pipe is splitting off into branches, isn't it? So here's the water flowing. It hits an intersection, that's an opening. Part of the water goes this way, part of it goes this way. Then this water continues. It hits another juncture. Part of it goes this way, part of it goes this way. So every time it's another juncture, you're going to have less and less water or less and less current. And we're going to see that today, that when we look at these parallel circuits, we're going to see how the current is a function of how many bulbs you have and how many intersections you have. Okay, that's so we can figure out what the actual current is in the circuit. Yeah.
So did you say that the first bulb in the parallel circuit will always be brighter than the last one? Or they
You
usually...
can't, and we'll talk about why you can't. It has to do with the actual resistance in the bulb.
Oh,
Okay, so we'll talk about that. For a series and parallel, they're a little bit different, but we don't want to generalize because of the resistances of the bulbs. Assuming all those bulbs are the same, we'll talk about that at the end, see what happens. Okay, I want to show you the laws first then. And there's a good amount here that we want to write down. Okay, so we're going to have a different part of each, and we're going to write a law or an equation for each of these. Okay, so can I get someone to read first? This is all about series. All these rules I'm writing down now have to do with series circuits. A series circuit. So can I get a reader for current, please? For current. Aaron, read current, please, for us.
Current. The current across each of the resistor is the same, like the flow rate of the water pipe through a pipe.
Okay, the flow rate of water through a pipe, exactly. So think about this. Remember, we're in series now, so if you need to actually think about it, let me pause and go back. The current is the same throughout because it's like thinking about water in a pipe again. If water were flowing through this pipe, even though it hit those load-bearing elements, it's not going to change the flow. It's not going to redirect it. It just slows down across that resistor, and then it continues. And it slows down a little bit, and then it continues. But the current in the system is constant. Whatever that current may be, we're going to figure out. But the current is constant, so we write down the following. I1 equals I2 equals ... IN. Who can tell me what that means when I write it like that? Why is the ... and the IN, mathematically speaking? Yeah, how many resistors could there be? Yeah, so the current across as many N resistors are always going to be the same if they're in series. If they're in series. Okay? Questions on that? That makes sense.
what's the N stand
What does the
for?
N amount of resistors, as many as there are? Okay? Where there are N amount of resistors. Second, voltage. Can I get a reader for voltage, please? Awesome. Dylan, go for it.
We could think about the fact that the potential difference across the battery is equal to the potential difference across the total sum of load across each resistor.
Okay, so think about it this way. The amount of potential difference that the battery is providing, say it's 9 volts. say it's 9 volts, listen. Say it's 9 volts. Part of that potential difference goes to each of the bulbs. And we drew a diagram of that the other day, where if there were 2 bulbs connected, it would be like full potential energy. It hits the first bulb, it drops. It then goes through the wires. The second bulb drops, and it has no potential now, and it comes back to the start. So what we can say here is that the total voltage is equal to the sum of the voltages. Okay? The sum of them. Whereas the first one, the current is consistent the whole way. You could put I in the front, you don't have to, but to be consistent with the way it's written. Okay? All right, finally resistance. Resistance, Nick. Nice and loud for us, Nick. Malaris. Yeah.
Resistance. Remember that V equals IR plus each resistor, thus for 2 resistors in series V equals V1 plus V2.
Okay, so now we're going to take a look at what this actually becomes here. Let's think about this for a second. If we had 2 different resistors that were in series, we remember that the voltage of the whole system is equal to the sum of the voltages of each. So let's say there's like a 9-volt battery. One bulb gets 5 volts. What does the other bulb get? Let's try that again. Focus. There's a 9-volt battery. One bulb receives 5 volts of potential difference. The other receives 4. Okay, because they're sum. They're the sum of them. So from that, what do we remember about Ohm's law? What is V really equal to? IR. So I'm going to write it this way. Oops, not V1, but I1, R1. Okay, start by writing this. We're going to go through where this comes from. It's very simple, the derivation here. We're going to come up with our resistance law from this. So that's the beginning point. Because again, V1 is really this. V2 is really this. This is the total voltage of the system over here. But what did we say a moment ago about the current? About the current in a series system?
They're equal.
They're equal. So I1 and I2 are the same thing, right? Again, the current in a series are the same. So I1 and I2 are the same. So that's what this becomes. Just call them I now instead of I1 and I2. What can I do if I have an I in both terms? Not square it.
Take it out.
Take it out. How can I take it out?
Factor.
What is it?
Factor.
Factor it. And then, yeah, in essence, Katie, we do end up combining now. We can combine the resistances now. Okay, we can combine the resistances. So what can we say from this? Let's take a look. We could say that the voltage of an entire system, okay, the voltage of an entire system and the current of an entire system results in the overall resistance being the sum of the resistors. The sum of them. And that's going to be our overall law there. That the equivalent resistance of a circuit in series is equal to the sum of the resistors. Okay, is equal to the sum of the resistors.
Does that say REQ?
REQ. And I put REQ to represent the equivalent resistance. So imagine if you had like 8 light bulbs lined up, right? Each of them with a resistance of like 20 ohms. Then you could put one bulb in its place with 160 ohms, and it would be the same circuit. Okay? It's an equivalent circuit. And that's what I was talking about with the TV. Remember with the TV in the example yesterday, we found the overall equivalent resistance of the TV. That's like finding the overall resistance of all the components. If every component in that TV was in series, you could just add their resistances together and get the overall resistance of the TV. But I'm telling you now that most, if not all things, are a combination of series and parallel. So we can't just use this law. We have to use this law with other laws as well. Okay? Yes?
What's VN and RN?
What is what?
VN and RN?
VN and RN? I don't see VN and RN anywhere in this page.
At the end.
Oh, RN here? Oh, these are nth amount. Sorry, nth amount.
Oh,
So like if there are 10 resistors or 11 or 12, it would keep going up.
it's like
Etc. Yeah, that's fine. You can think of it that way. But you should be familiar with this from math. like a series or a sum, if it was like 1 plus 2 plus 3 plus dot, 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 like you're adding all the integers together, you would say, A1 plus A2 plus A dot, 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 AN, meaning the nth amount. All right, well, think of it as many resistors as there are. That's what N would be. If there were 10 resistors, there'd be R1, R2, R3, R4, R5, 6, 7, 8, 9, R10. Yeah, and it would be an ohm still. Yep, that's right. All right, that's series. Let's take a look at an example of series. We may only get through series today, and maybe we'll push back the parallel ones for the next class. Depends. All right, so an example. A 9-volt battery is connected to 4 light bulbs as shown in the figure to the right. Okay, this is the example we talked about where there's multiple bulbs connected. Draw a schematic representing this, then find the equivalent resistance for the circuit. From this, determine the current in the whole circuit, then find the voltage drop across each resistor. So there's a lot. Step 1 on your own, please. Go ahead. Draw a schematic. Draw a schematic. On your own, draw a schematic. Think of what you would get from this. I want you to practice it. So practice on your own. Use your symbols for light bulb and for battery just to draw a simple schematic for this. And don't be discouraged if you're not right, please.
It's supposed to be straight lines, right? Not squigglies.
Well, that's the diagram. That's the picture. You can draw it the way you think it should be, yeah. If you need to look at your diagram, go ahead, or your symbols in the previous slides. Anybody want to draw theirs?
Are those blueberries?
Snickleberries?
Just that berry.
Wow.
Oh, I missed the light bulb.
What is it?
What'd you get?
Who's drawing that?
Oh wait, does it have to be like that? I just put it in.
Drawing with my mind.
Like that?
Yeah. Now I'm going to put a plus sign in the big terminal with my mind over it.
Alright, who's
I'm going to put a plus sign right there. Oh, it didn't work.
That's so cute, you're so
Wait, we need a plus sign right there?
No, you don't. You're supposed to follow along.
Oh.
So
Yeah,
who's
that
drawing?
was pretty
I'm
simple.
trying to make it
Yeah.
So-
Madi.
Yeah, thank you. Perfect. Now, does anybody have something different? And the answer is you could have something different. So does anyone's look different? Be honest, does yours look different? Okay. All that matters is this. All that matters, and it could look different. All that matters is that you have a positive and negative terminal, that you have 4 bulbs connected in series. It doesn't matter if your positive terminal is down here. Or he could have drawn his positive and negative terminal over here. Or he could have drawn the positive one as the lower one and the negative as the upper one, like that. It doesn't really matter which of those. Okay, it doesn't matter which of them. All that matters here is that we have a completed circuit with a power source and 4 bulbs in series.
Looks like a truck.
Okay, looks like a truck. Yes, it does actually. Yeah. All right, so that's step 1. Good. Step 2. Step 2. Find the equivalent resistance of the circuit. So I want to do this. Ready? And it's amazing that we can just do this. I just want to do this. And imagine there was only 1 bulb now. Okay? Imagine there was only 1 bulb. If there was only 1 bulb, what would its resistance be? I'm going to label all these, by the way. What would it be? 7? 2? No. If we replaced all 4 bulbs with an equivalent bulb, look at your previous slide, what would the resistance be? What is the rule for resistances?
6 plus 5 is 11 plus 7 is 18 ohms.
So altogether we're going to
Where do you get those numbers?
add them up. Remember the rule. The rule for resistance in series was this.
There's no 6.
4 plus 2 he did. Okay, here's the rule in the bottom right. The rule for resistances in series, and these rules are on your formula sheet. Look at your formula sheet so you know that they're there at some point. Okay? You have to be able to apply the rules though, obviously. Okay, but the rule is that when you add the resistances together, you get an overall single resistance. So that's where the 2 plus 4 plus 7 plus 5 becomes 18 ohms. Okay? That's step 1. Step 2 says, from this, determine the current in the circuit. Determine the current. What do we know about current? What's the rule for current in series circuits? Current is the same, right? No matter what. So even though I made this a new circuit, the current that's here was the same as the current. Oops, I should really draw it this way. Oh no, we talk about positive flow actually, right? Even though the electron moves that way. Okay, the current in these circuits are identical. So if I want to figure out what the current in the whole circuit is, I can look down at the bottom here and say to myself, I've got an overall resistance. Right? I've got an overall resistance. What's my voltage of the whole system? 9 volts. Whose law or what law could I use to find the current? What is it? Yeah, take a look. We've got the equivalent resistance, it's 18 ohms. We've got the voltage of 9 volts, and we'll solve for the missing current. Okay, so V equals IR, Ohm's law that we looked at, it's going to apply in all these equations. All of these calculations, Ohm's law, we're going to use over and over again. Whenever you find an equivalent resistance, you can then automatically find the current through it by doing V as the battery equals I, the current, times R, the resistance.
Would you find the current first and then solve for
How could you find the current without the 18?
I'm saying like the other way around, so solve for I, we solve for R.
But think about it. How could you find the current if you didn't know what this R was?
If they gave it to you, like if they give you
Well, that's different. If you're given current, you might have to find the overall resistance, sure. Yeah. But you're not in this case, right?
No, I'm just asking if it was okay.
What you...
Maybe they'll just give you I and R and then multiply.
Yeah. If you're given that part, yeah. But traditionally speaking, you're going to find the equivalent resistance and using that equivalent resistance be able to come up with the current. Okay, come up with the current. Now, the current in this case would be what? 0.5 amps, right? Half an amp. So if that current was too much for this load-bearing element to withstand, it would blow out the bulb. That's how a bulb blows out, and I was mentioning this before during the break. And we were talking about the idea that when a light is turned on, it's cold, so it's got a very low resistance. If something has a very low resistance, the current passing through it could be very high. Okay? Once it warms up, the bulb gets hot, resistance increases with more temperature. If resistance increases, the current goes down. So the biggest chance of a bulb blowing out is right when you turn it on, every time. Because it's got such a low resistance when it's cold in the bulbs that the current can be really high, and a supercharge of current will cause it to blow out. So if this current was too much for this load-bearing element to handle, this bulb would blow out. So maybe what you need to do is do what if this isn't good? How could you change something about your diagram? Or what could you do to the circuit to make it a smaller current if you needed a smaller current? Put more bulbs, more resistance, yeah. Put another bulb here, right? Put another bulb. What would happen to the resistance? It would go from 18 to something higher. If 18 is here, and you took 9 and divided by 18, but then you take 9 and divide it by a number like 36, 9 over 36 is 0.25, isn't it? So as you increase the resistance, you're decreasing the current. Okay, that's where the whole idea comes into play. And a lot of the time, your voltage is fixed because it's your power source. You're not alternating or changing your voltage. The last part, the last thing we have to do, and this is, I find to be amazing, the way it works out. Find the voltage drop across each resistor. Remember, not every bulb is getting 9 volts. Every bulb is getting a little bit, right? The whole thing is 9 volts, but every bulb is getting a little bit of voltage. So let's think about this. The first element, what's its resistance? The first element going in the order that I drew. What is it? 7 ohms, right? In the order I drew, guys. Here. So 7 ohms is the first one. So R1, the first bulb is 7 ohms. What's the current through the first bulb?
0.5.
Why? How do you know?
Because they're all the same.
Yeah, remember current is the same throughout. So the current's going to be the same for all of them. R2 is 5 ohms. R3 is 4 ohms. And R4 was 2 ohms. And the current is the same for all of these. So, tell me something. Which of them is going to have the highest potential difference or highest voltage drop across it? Across it, at least.
R1.
Why?
Because 7 times 0.5 is higher than the rest.
Exactly. Remember, Ohm's law to figure out all this stuff. If you now want the voltage across the first element, you make that V1 and use R1 and use I1 to get the voltage across the first light bulb. Well, that happens to be 0.5 times 7, which is 3.5 volts across the first one. What's the second one? You can do this in your head now. The third one, we take 4 again, multiply it by 1/2. And then finally the last one is just, okay? Sum them up, please. Sum them up. What do you suspect it might be? 9 volts. Remember that theory we went through the other day? How the charge carrier leaves one of the nodes with a lot of potential energy and it gives it all up to the light bulbs along the way? At the end, it's got to have no energy left or no voltage left. Add these 4 up. After it crosses the first resistor, it loses 3.5 volts, leaving behind 5.5 volts for these 3. Then it takes on 2.5 volts for the next one, leaving behind 3 volts for these 2. Then the third resistor, or the third bulb, takes on 2 of those volts, leaving only 1 volt of potential difference, or in this case you can say energy for now, okay, for the fourth light bulb in the circuit. Okay? In the lab, we're going to talk about brightness, and I don't want to answer that question yet because I suspect some of you might ask it. I want you to figure it out on your own in the lab. Okay, so we'll talk about how brightness is affected and stuff. That goes back to power. Remember that power is IV. Remember P equals IV. So it's a little bit different here. You could start guessing as to what it is, but I don't want to go into the actual answer just yet. Okay? Let's see. We mentioned this already. If one light goes out, they all go out. So if there's no filament in that one bulb, then the electron would continue to move. It would go through all these bulbs, then it would get here, and it would stop right here. Okay, so since there's no circuit established, there's no EM field. If there's no EM field, the electron wouldn't even move at all. Again, you have to have a circuit closed to create a potential difference or an EM field. If there's no EM field, it's not going to push it along the way at all. Okay, I might pause there for today. Let me see if I want to stop there. Yes, I'm going to stop there. Okay? So a 9-volt battery is connected to 4 light bulbs as shown in the figure to the right. Okay, a 9-volt battery. Take a look at the way it's connected. These are in parallel. It connects to one bulb, loops, 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 and then they all loop back. It's not going through the bulb, going around. So if I were to draw this as a schematic, right, draw as a schematic, I would have a battery here. It would hit the first bulb and come back. Second bulb, come back. Third bulb, and fourth bulb. That's what this is as a schematic. Okay? The first resistor is 7 ohms. Second is 5. Next is 4. And next is 2. Notice these are the same numbers as last class, these resistors. But the results are going to be very, very different. Okay? So same resistors, but instead of being in series, now they're in parallel. So what we're going to do here is we're going to find the equivalent resistance of the system. Again, find the equivalent resistance. So to do that though, I need to use that new resistance law. So what would that look like? What would that look like? The last thing we had on the last slide, but plugging in these 4 resistors, what would you have as an equation? I'll give you the generic form.
It'll be 1 over 7 and 1 over 5.
Okay, there's the generic form. And this is not difficult, but the math could be a little tricky, if anything. So what do you got, Tristan?
1 over 7 plus 9 over 5.
Okay? And now the tough part here is this. We need to solve for the equivalent resistance, which is in the denominator, right? Now, it's difficult, not difficult, but it's really messy to find a common denominator here, because it looks like 35 might work, but 35 is not a multiple of 4 or 2. So it'd be annoying to find a common denominator. So here is my suggestion. Take out your graphing calculator, please. Now, add these 4 fractions together, making sure you put parentheses around them. Add them together. You're going to get a decimal. Don't round. Just tell me what your decimal is. Give me like 5 places. Leave it in there in your calculator. All right. There's a bunch more probably after that. Now, that's what you get when you add the 4 fractions together. That is not REQ. That's 1 over REQ. If it's 1 over REQ, we need the inverse of that, right? Remember the inverse or the word reciprocal? If I wanted to get REQ, I have to flip this, don't I? Take a look up. If I want to get REQ, I have to flip this fraction. So technically, I need to take the reciprocal or inverse of this. There's a button on your calculator. It says x to the negative 1. Just press that. It'll take your answer and raise it to the negative 1 and hit enter. Okay? It'll take your answer, raise it to the negative 1, and hit enter. What do you get for REQ as a result then? Give me 3. 0.915. Okay? Notice that this fraction was equal to a number bigger than 1, so the inverse of this is smaller than 1. Okay, that always happens with reciprocals. If the original number is greater than 1, the reciprocal is a fraction or a decimal. Okay? That's the equivalent resistance of the whole system. Resistance of the whole system. What do you find interesting about that? What is interesting about that? It's lower than any of the originals, right? The original resistors were 7 ohms, 5 ohms, 4 ohms, and 2 ohms. And when they were in series, we just added them up, and the number got bigger. But here, we're saying that it's equal to all of the reciprocals. And when we do the calculation, this equivalent resistance is smaller than any of the 4 resistors. That will always happen in parallel. Again, in parallel, REQ will be less than any of those individual resistors. Okay? You can jot that down, that's a good thing to know. Whereas series, you just add together the 4 numbers, and the REQ you get is bigger than any of the original 4 or original resistors. Alright, the next.
So you said the other one is called what?
Series.
Series and it's called
Parallel. Let's look at the next part here. From this, determine the current in the circuit and then the current through each resistor. Okay, let's find the current in the circuit and then the current through each resistor. If I want the current in the circuit, I need to remember Ohm's law. And remember that, really, if I want the current in the whole circuit, I'm looking at this simplified circuit here. So if I want the current in the whole thing, Think about if you took all 4 of those resistors and simplified them into this one resistor here. Use this quantity, use the voltage you have, and come up with the current in the entire system. It was a 9-volt battery. Again, it was a 9-volt battery. So voltage equals 9 volts. The resistance of the whole system is 0.915 ohms. Find the current in the whole system by dividing. You should get 9.8 amps. Okay, 9.8 amps of current. Somebody look back in their notes and find the current when we did this in series. Go back to the example 1, I think it was. Yeah, example 1. What was the current when it was in series? 0.5 amps, right? Really small current in series. Really large current in parallel. Remember how I said to you, it's important when you're making a circuit to know how much current you have. If there's too much current, the wire will heat up and you're going to short circuit. So if you need to lower your current, you want it to be in series. If you want to bring your current up, you want it to be in parallel. Let's jot that down, please. Okay? So again, if you want a low current, it's highly useful to have it in series like last class. But if you have a current, if you don't mind the current being really high, okay, you can use parallel. Now the last part of this question said to find the current across each resistor. I hope we're focusing and we can minimize the chatting that's clearly going on. Here, we can find the current across each resistor. Now, look at the original setup. We've got 4 different resistors. Okay? The voltage across each resistor, though, is the same. Remember, in the previous slide, we said that V equals V1 equals V2 equals V3, etc. So the voltage across each of these is the same, but the resistance is different. So find the current 4 times here, and then figure out, like last class, okay, that there is a relationship here. Say again?
Those exact resistance numbers, for 22.
Louder.
The homework 22, I think, was the question. It's exact.
I'm sure they're different, the numbers. Maybe they're the same, maybe it's a different voltage source, maybe they're arranged differently. So if I want to figure out the current through each of these, so let's look at the first element. We did this last class in series. Okay, same thing we're doing again. Look at the first element now. We want to find the current. So we're looking for I1. The voltage across all of these is the same because it's in parallel. So the voltage is going to be 9 volts across them all. What was the resistance across the first light bulb? Look at the diagram in your notes. What was the resistance? What was it? 7 ohms. Good. Okay, so solving for I here, what do you get for I1? 1.3? Agree? Others? Let me look at mine. Yep, 1.3. Very good. How about the second one now? What's going to change? What's the only thing that's going to change on the second resistor? The resistance. Yeah, this is 5 now. This is still 9. So do 9 divided by 5 now. And give me the second current. Anybody? 1.8. The third resistor has a resistance of 4 ohms. So do 9 divided by 4 now.
2.25.
And Del on the last one?
9 divided by
4.5.
Ooh, he beat you. Do it in your head. 9 divided by 2 is 4.5. Here's 4.5. You got them on the last one. You'll be all right. Add those numbers together, please. Add those 4 numbers together. And what do you get when you add them together? Approximately. You got 10 exactly? Okay, so we rounded a little bit. You got what? 10.1? Yeah, if you kept a few decimals, you end up getting around 9.8. Okay, it is the exact value really. If you kept infinite decimals everywhere, earlier, remember how we rounded? When we did the inverse, we rounded it to 9.8 amps. This would have a few more decimals. If you kept all these decimals for each of them, it'd be a lot more. Adding them together though, you will get the overall current in the system. Why is that? Why when I add the current across each resistor, do I get the overall current in the whole system?
Isn't it just the sum of all the current?
Yeah, the law was it was the sum. That's exactly right. This was the law for current in parallel. We wrote this down a minute ago. It's in your notes on the previous slide. This just proves this. Okay, the sum of these 4 currents is equal to 9.8, the overall current in the system. Okay, so this is always going to hold true in parallel circuits. Any questions so far? Any questions so far? All right, because we're going to jump right to 23, which is we already made this statement that if we cut out one of the bulbs, the flow still continues because the circuit is still complete. See, that's still complete, that circuit there. The next circuit, skipping the second bulb, is still complete. So when you cut out a bulb in parallel, the rest of the bulbs still are lit up. This was that example that somebody mentioned, the Christmas tree. If one bulb goes out, the rest don't go out anymore. Old Christmas tree lights, they used to all go out, right? If you pop one bulb, they would all go out. Those were made in series. Newer ones are made in parallel. Quick summarization of this. In series, this is what it looks like. In parallel, this is what it looks like. And this is what we saw already. The current in series is the same across each resistor, but in parallel it's the sum. The voltage is the opposite. In series, the voltage is the sum, but in parallel the voltage is the same across each resistor. The resistance is the sum in series, but in parallel it's the reciprocal sums. The reciprocal sums. This is your summarization. These laws here and here are on your formula sheet. Okay? So be familiar with them, please. Load 23. 23, we're just doing one example. That's it. Okay?